And this short session is going to introduce you on how to estimate the resources that you need when using HPC systems at the university. So in these materials, we're going to cover some basic concepts about HPC systems, just to be sure everybody's on the same page. We are going to see how to run small benchmarks of our code, and then how to use simple command line tools to monitor the amount of time that our code takes. Also, maybe some slight information about the amount of memory, but here by resources, we are mainly going to focus on hours of computation. Finally, we are going to see how to convert the results that we get from our benchmarks into an estimate of how long it will take our execution of the program. So prerequisites for the materials, I hope that everybody is familiar with the use of the command line. So it's a very basic need when you're using HPC systems. So if you are not familiar, we have a course as well on the use of the command line. So basically, it's the same URL here, Crystal Training, Intro, CLI. So this will take you to an introduction course of the use of the command line. So if you are still beginner and you want to have a look into it, I'm sure that you will be beneficial for your research. And I expect that you have some kind of project in mind. So you want to run some specific code or program in HPC systems. That is the one that you want to benchmark. So let's start by some basic concepts. Here we're going to talk about like core hours. That is the total amount of time that it takes a program to execute. That is going to be approximately the wall clock time. So basically you can imagine wall clock, we mean that real time. So as you look to your wall and you see the big clock there ticking, multiplied by the number of cores that your program is using. So if your program takes 1 hour to execute and it uses 4 CPU cores, the total core hours that your program needs is going to be 1 times 4, so 4 core hours. Here you have another example. If your program uses 2 hours using 8 cores, the total amount of hours, core hours used is 16 core hours. By CPU time, we understand that the amount of time that the CPU is running your code. This could be like kind of equivalent if your program like starts using all the cores at the same time and don't have much interruptions in terms of trying to access files and needs to wait to get the data loaded and so on to the wall clock time. But we need to be aware that sometimes when we read files or so, CPUs need to be there waiting. So this time usually is smaller than the wall clock time. Because in HPC systems, we are going to use a scheduler. We are going to talk that we have tasks. So this is an independent program that we want to run or code. And then we have jobs that this is when we submit our task to the schedule, it will create a job to run it in the system. Jobs usually are defined with kind of scripts, and there are some parameters that sometimes you can run multiple tasks inside the job with different parameters or arguments when you call the command. So this is why we say that sometimes jobs may contain multiple tasks. If we are running a program that uses just 1 core, of course, we will have that the CPU time used is approximately the same that the wall time, just with a small difference that we may have some interruptions for access disk and so. If you are using more than 1 core, the CPU time, as we saw before, is the wall time times the number of cores that you are using. And the heavier is the use of more input-output, so the use of disk, for example, the wall time is going to be larger than the CPU time. We're going to see in next sections that we are going to use this command time. This is a GNU standard command to monitor the time that the program takes. And you will see that when you got this output, this is broken down in these different times. The lapse time, this is the wall clock time, the kind of real time that it took the program to execute, in this case 2 minutes 15 seconds. Then we have the user time. This is the time of CPU usage that we did. Then we have the system time. So this is the time that mostly the program used for input output, and maybe sometimes to load some libraries from the operating system or kernel and so on. So in this case, you can see that there's a small fraction of this time, that like 12 seconds versus the 120 seconds of execution time that was used for these kind of operations. And you will see that this program as well, it gives you as well the maximum amount of memory, like the peak amount of memory that the program used during the execution, in this case in kilobytes, but it's like around 2 gigabytes. So it's important to understand these very basic concepts just to be able to efficiently use these HPC systems, and why it's important to get these kind of precise estimators of execution time and not just kind of guess approximate numbers. First, because if you make a guess and you are based on how long it takes the program to run in your computer, you are ignoring that HPC systems, sometimes they have much more powerful CPUs than your laptop or desktop. And what it takes 1 hour in your laptop, maybe it takes half of the time to run on the supercomputer. So you are overestimating the amount of resources that you need. Be missing parallel opportunities. So maybe in your own machine, you have 4, 8, 12 cores, maybe 24. But maybe when you move to an HPC system, you can use their much larger amount of cores, maybe 64, maybe 128, so much larger number that you are using in your system. And we need to consider that, of course, when you submit jobs into scheduler and so, it takes a little bit of overhead of time. So that also may impact the way that we estimate the amount of resources. So what are the best practices so that we need to do? First, as much as possible, run our benchmarks that we are going to see in the next slides in the target system. So you get accurate times in the system that they are going to run. Try to use data as close as possible to the data you're going to run in your analysis. If you can just get a subset of the data that you're going to analyze, probably is the best approach, because sometimes the behavior of programs depends on the input data as well. So it may take longer or shorter depending on the data that you give to the program. So it's important to give something that is going to be as close as possible as the data you're going to analyze. We want to get these estimates as accurate as possible. So based on the using of benchmark and passing to these benchmarks the right amount of the data as close as possible as the one that we are going to analyze. We want to get real measures from the system. And we need to account always for some variability. Even if we pass some random sample of our data, that may have not captured all the variability in the data, and it may take slightly longer than expected. So we don't want to fall short. Or if you are writing your own programs or code and you are not sure that the initial versions are going to be correct, maybe you want to account as well for some margin of error to be able to run some tests and repeat some of the executions and so on. Let's see now a bit just the basic concepts of what are scaling laws. You can have programs that behave in a linear way. So if you give them twice the data as an input, it will take double amount of time to execute it. So this is very flat line here at the bottom. So things are growing linearly, and it's very easy to extrapolate the amount of time, because basically it's just multiplied by the difference of the amount that you increase the data. But then we have other behaviors. This is just an example. It can be different shapes of the curve. But if we think that's something that scales quadratically, if you pass twice the amount of data, you will get at the time it didn't grow 2 times, but instead it grows 4 times. And if you pass 4 times the amount of data, the amount of time will not be 4, will not be 8, will be actually 16. So it's running quadratically, as we see here in this curve that grows very fast. So here you have an example of some execution of a program. For example, here we have said that this program, just a fake program, just dummy example, we pass some data as an input in a CSV file, and this data set is just a test data set that it contains 2% of the sample that we want to analyze. Then we execute again this same program, passing a 4% of the sample size, and then again passing an 8% of the sample size. So if this grows linearly, we will say that this is our baseline. So if we pass twice the amount of data, so from 2% to 4%, we should expect that it takes twice the amount of time. If we pass 8, compared to the baseline is 4 times more, so it should take 4 times the amount of time. If it takes longer, for example, it takes 10 times longer when you use an 8% of data compared to a 2% of data, then we will have to be aware, because things are not scaling linearly, and we need to kind of estimate what is the curve that our execution follows to try to make an estimate of the resources that we need. We're going to see this right in the next slides. If you're running code, and I probably nowadays most of you will run code that uses more than one CPU core, we need also to be mindful of Amdahl's law, that basically it says that if you can parallelize maybe 20% of your code, you will not expect more benefit of using multiple cores than that, reducing that 20%. So that makes that using more cores not always translate to a direct speed up. So going from 2 to 4, it doesn't go to 4 times speed up. It was maybe to 3. First, sometimes there are extra overheads in the sense of setting up the right parallel data structures and sharing data between cores or different nodes. Also, because as I said, there's just a fraction of the program that can be parallelized. So there's also a baseline there that it takes always the same amount of time. So that limits the speed up that we can get from our code. In some instances, you will see that that's not the case, that you can get almost linear speed up. That's possible, particularly if your program have kind of grid topology, that you can just divide a large data set into smaller fractions and run all in parallel because there are no dependencies. You will see that you can get quite close to a linear speed up, but in other instances you have to be mindful that just for giving more and more number of cores, you will not get a direct benefit in the same amount of speed up. So it's always a trade-off between balancing what is the speed up that we have or we gain giving more cores. So how we can test this kind of scaling, and this is advancing what we have in the next slides, that is just running some kind of a small benchmark. So let's imagine that we have a small script that we want to run our program passing this data set, my data, and we want to check how this scales with different number of cores. And we assume that our program can't use this option here, that we pass the number of cores that we want the program to be using. And when we execute the program, we pass as an input our data set, and then this parameter number of threads, number of cores, and we save our output of running this command time that it captures the amount of time used for the program that, as we saw before. We save this into a log file, a txt file. Just note that if you are using this and you want to save the output of time, here it's have this redirection to a file, and this is the standard error output. So be mindful that you need to capture the error output, not just a standard output. So assuming that we have run this, we can have something like this, for example, that our program took, using one core, 120 seconds, 2 minutes. When we use 2 cores, it took 65 seconds. So quite close to a linear behavior, but just this 5 seconds difference. Then we have that when we execute this with 4 cores, speed up starts to slow down, and the efficiency was like 86%. And when we are using 8 cores, things are not so efficient anymore, and we go down to 60%. It's still not bad. I will not say that that is something that we will not to use this amount of resources. This 60% efficiency is still quite decent, but of course, maybe will not justify then going to 16, then maybe we will go down to 40% efficiency. There's always this trade-off that you need to do depend on the amount of resources that are available in the HPC resource that you are using. As well, be mindful that these resources are shared with other users. So sometimes it's trying not to be a bit too greedy for getting very little benefit on your execution. So let's see a bit of how can we implement some small benchmarks. So we're going to see here how to run some very simple benchmarks of our programs. I just want to acknowledge that the setup that I'm presenting here is kind of a very basic way to run benchmarks. Depending on the programs that you're running or the system that you're using, you may have some profiling tools that may give you much in detail information about the execution of your program, being the CPU hours or the memory usage or so on, or even sometimes the time used for each different part of the program. But in this case, we are going to keep things simple and try to be helpful for everybody. The same principles will apply if you're using more sophisticated programs. This very simple setup will showcase how to do it. So first of all, the workflow that we are going to use is we need to create some kind of test cases, some way to select smaller data sets that we will use to estimate the time that our program takes. We will run our program with these different data sets, different sizes, and estimate the time and maybe the memory usage that they do. And then using this data, we are going to calculate the amount of resources that we need if we use our whole data set. Top tips. This is kind of very general in terms of good practices in reproducibility. Document your environment, what software versions you use, what modules, also the system that you are using, and try to run end-to-end tests. So all the same execution that you will run in your complete simulation, do it as well when you run the benchmark. Sometimes missing some parts of loading or storing the data may have an impact on the time estimates that we have. So the basic tool that we have already seen in previous slides is time. And basically have a very simple syntax. We need to just call time, and then we can just type the same command that we are going to use to run our program. Maybe specify -b. I think that is like verbose mode, so it gives you extra details. But if you want to customize the output of the command time, you can as well pass exactly the values that you want to retrieve. In this case, the world time, the user time, so the CPU time, system time, so mostly time used for input-output, and accessing disk. Max resources is amount of memory that the program uses the peak amount of memory the program uses. And then, as before, the name of our command that we want to execute, and maybe parameters like the data that we are going to use. Let's see this in a practical example. Here you have a small script that uses a for loop to run the same code execution with three different percentages of the data, 2% and 4% and 8%. So basically this for loop, apart from printing here a message, it calls the function time. We request to get runtime, the world time, user time, system time, and memory usage. And then we call our program with its arguments. So in this case, just a dummy name, my simulation, parameter input we want to use. That is data underscore and 2, 4, or 8%.csv. And then there have as well some output file to save some results. This is going to be saved in this log file. And after we will use the data there to estimate how the time grows based on the amount of data used. Of course, here I use a for loop. If you don't like to write scripts in this way and you want to keep things much simpler, you can just straight run this call to time, passing your program and parameters just directly without making it inside a for loop, and of course saving the results somewhere. Just a little warning here that depending on your code, if they have some kind of sources of variability or your amount of data is relatively small, so if the execution can change from execution to execution, the execution time can change from execution to execution. We may want here to introduce another nested for loop to repeat each one of these calls to a program with different data percentage multiple times. In this case, for example, suggesting that we could include a for loop here to run things 3 times instead of just one, to be able to capture this source of variability and maybe later just use the average of these 3 times, or maybe use the max time use in any of these executions. So let's see a very simple example. Imagine that you have a program that analyzes some images, and the basic behavior of the program is that we load the images from the disk, we run some algorithm that detects the objects, and then we save the results. And we have 10,000 images that we need to process. So given the large amount of data as input that we have, we may want to create like smaller subsets just with, for example, a 5% or 10% and a 15% of the data. And in this case, we are going to use a command called like shuffling a txt file. So imagine that you have this txt file where each line have the name of one of the input files. And here basically this command selects randomly 500 of the lines of this input file. And after we save this in this other text file uh, in this folder for 5%. And we repeat this for selecting a 10% of the data and then a 15% of the data. You can see here that we are sampling things randomly, and as we acknowledged before, this is to make sure that the data gets as close as possible to the data that we are going to analyze, so we are not missing some variability due to the input file. Then in this example, we can run we can write a script to submit to the system, and as we usually need to do in HPC systems, we need to load the packages, the programs that we use. Then we will run this for loop for 5, 10, and 15% of the data size. And to account for some variability, as we acknowledged before, maybe we want to repeat this like 3 times for each one of the sample sizes. And then here inside, we call the function time. We pass these values just to customize the output, but this is optional. And then we call our Python script, just calling Python, the name of the script, and then parameters like input data set, that is going to this one with a percentage size here as a value, and then we will save the results in this other file. Everything is going to be stored in this timing results.log file that I want to just put emphasis that you need to save this from the error output. If not, if you say just standard output, you will not get these values. Here, there's an example of this output file. For example, we have that is printed that for 5% of the data, the first run, it took a wall time of 2 minutes, 15 seconds, and user time of 2 minutes and 1 second. Approximately the same for the second run, and then we have here that for a 15%, for the first run, it took 4 minutes 45, and the user time was 4 minutes 15. So plotting this, or plotting or just depicting this here, the values you see, I mean, you cannot see the complete list, but imagine that you have that for a 5%, it took 135 seconds. So 2 minutes 15 seconds that we have here. Then for a 10%, it took 285 seconds. And for a 15%, it took 580 seconds. So this basically scales very linearly. And if we extrapolate this linear scale from 5% to 10%, so basically you can imagine this is 10, so we can multiply this by 10. So it will be approximately 2,850 seconds. That is approximately, I think this value is incorrect. I think it's 47.5 minutes and not 27, but it's gonna very easy to do this estimate. What happens if things are not linear? Well, I mean, one thing to deal with this is as simple as going to Excel. You create a small table with your data that you capture. So what is the percentage, for example, of data size and what is the runtime that it took? And you can ask Excel to just create the estimate and display the equation of it. In this case, I think that this is like just a polynomial estimate. And you can see that the fit is relatively close. And based on this equation, you can just calculate what is the estimate, or even visually, you can ask Excel just to extend this estimate to 100%. And you will see that here, more or less, we can see that this will take about 5,700 seconds, so close to 6,000 seconds. That basically it's like 100 minutes, so close under 2 hours. So now thinking about particularities of benchmarking things on your HPC system. First of all, just acknowledging or putting emphasis that you should not run your benchmark in compute nodes. Even you think that it's going to take just a few minutes, they are logging nodes, so they are meant to be used by people to log to the system and be able to use the system. So if you run things on the logging nodes, you put the system in danger to be blocked by other users. So that's something that we always need to avoid. If you need to run things interactively, I'm sure that all your systems, they have some ways. I think that this is the way that most of the systems here in Bristol they use. So you can request an interactive session with salloc. And then when you are inside a node, you can use srun to run your programs. And here, of course, we are passing as well the time command to be sure that we capture the time used to execute this. But I would expect most of you need to use jobs. So this is a standard formatting of jobs that you probably know very well. Reminder that you need to have a specific project account. So you need to pass here the project account. You have to select a partition. In this case, probably test partition is fine. You need to give job a name, whatever you want, in this case, benchmark. And then if there's some output that the program prints, you may want to capture here with this benchmark out and benchmark error. So if you don't redirect the execution of time into a file, I think that probably it's going to go by default to this file. But if you redirect to another file, it's going to be probably just in the other file. You need to specify the number of nodes that you're using, the CPUs that you're going to use to run your program. If you know the upper bounds limit that you need, specify it as well. And if you have a wall time, a total maximum that time that your program will take, it's a good practice to as well to add it, just to be sure that things don't run there for a long time if it's just an error. Then we load our models, in this case Python, for example. We set up some variables, maybe defining how many threads we want to use in this code that it seems that is parallel. We print some messages on the screen, and then we call the function, the command time. We can call as run or just call directly the program. That's fine, and then say that we want to execute Python my program.py, so a script in Python. I'm passing the input data that we want to use. In this case, a kind of 10%, and they have here in this case a parameter that indicates the number of cores they want to use. This is going to be very specific on the program that you want to run or the code that you want to run, so you have to customize all this part, that what is the command or code that you want to execute with your own parameters. Once we have done that, you will have the data in your log file that you saved. If you want to look at the time that some jobs that already run took, is it possible to look at the jobs run, I think probably last few weeks or even months, using the command sact -j, and then you need to specify the job ID. So you need to know the job ID of the execution you had, and then indicate what parameters you want to see. In this case, job ID, but also the elapsed time, total time of CPU usage, and maximum memory use, request how many CPUs or cores, and then the state if it was run and completed or still running, for example. And here you have this data extracted just a bit nicely formatted. One of the questions we had the other day when we ran this session is what happened when you use GPUs. Here we are talking mainly about CPUs. GPUs is slightly more tricky to monitor the usage, but there are tools out there. But generally the same principles apply. So if you estimate that with one CPU it takes some amount of time, and with two CPUs it takes twice the amount of time, maybe that points that things scale linearly. Just acknowledge that GPUs, the architecture is a bit more complicated, and sometimes they are not so efficient when you have small data sets. So you may need to consider having larger data sets when you run some benchmarks, because they have longer warm-up times. And this is due because sometimes they have overhead for transferring the data to the GPU, and as well, it can have effects on the byte size that you're sending, and so on. So this is something that if you are a GPU user, you need to take into account when you do your estimates. Just a more small revisit how to convert our estimates to resources. So first of all, we need to select what is or decide what is the scaling model based on our results. So this is what we saw with the linear behavior and with the quadratic behavior in that example, that non using Excel. We need to be mindful that we are using the optimal parallel configuration. So don't if we run our benchmarks, and of course we don't want to run our benchmark with thousands of GPU cores, but we just want to use a few amount, we need to be mindful of what is going to be the final optimal parallel configuration. With this we calculate the number of core hours. Also, we need to be mindful if we need to run things more than one time. Sometimes programs they have multiple parameters, and we want to run for a set of different parameters. So we may need to account as well how many runs of each one of the codes with a different parameter we want. And be mindful of adding, as we mentioned before, some safety factors. If we think that our code have some variability in there, if we think that we are kind of in a very early experimental phase in our project, we may want to allow time for development on some errors and so on. Here we have an example. For example, we want to run this program, climate sim, so some simulations of climate. We are going to use 20% of our data, and we expect to use 8 cores, and they will have a, says that efficiency of 75%. And we measure the time, and it says that it takes 45 minutes, real time, world time. And we expect things to scale linearly because it's kind of grid problem, so there are not much dependencies, so we can scale things easily. And we have 50 different configurations that we need to take into account. So we are going to repeat some of these simulations with 50 different sets of parameters. So we need to convert first from this 20% data set to 100%. And this is assuming that it scales linearly with the data size, of course, that is going to take 5 times longer. So if the original time was 45 minutes, multiplied by 5 is 225 minutes, so 3 hours, close to 4 hours. And this is the world time. So now to know how many core hours we are going to use, because this is the real amount of resource that we need to multiply this by the number of cores. In this case, we said that we are using 8 cores. So the number of core hours that we are going to need is 30 core hours. We said that we want to run this with 50 different sets of parameters of configuration. So 30 core hours times 50 in total is 1,500 core hours that we need. Last bit, the safety factors. Maybe we want to allow for some errors. So maybe we want to add this 40% of time that allows for us to repeat some of the simulations. Maybe this is a simulator that we are still developing, so we want to allow time and acknowledge that we may have errors that we need to repeat things on. and on. So maybe we want to use double amount of time just to be in a safe space. And because we acknowledge that there may be some variability or difference when you scale up the problem with the full data set, we may want to allow this 20% extra of time. In total, if you sum this, just mindful that baseline is 1, so this is 0, 4, 1, and 0, 2. So in total is 2.6 times more. So we multiply this by 3.6, so plus 1, 2.6. And that brings us to the total estimate that we are going to need 5,400 core hours. Uh, Safety factors are kind of difficult to define, so be mindful that when you request access to a project in Bristol, you are going to be able to, if you run out of time, you are going to be able to request an extension. So it's always a balance to try to manage what is the reasonable amount of resources that we are going to use without being too greedy or just requesting too many that after are not going to be used. And that's everything for these materials. If you have any questions relating to this, please feel free to write us at JGI Training at Bristol AC UK. Also, if you have other queries related to HPC, you have this mailbox, hpc-help at Bristol AC UK. And thanks for listening, and hope to see you in other training soon.